1, 2, 4, 8, 17, 35. I mean, how would you characterize this curve? If I increase just one of my steps, then I can double the number of elements I can take on. First, I'm going to flip this horizontally, and then I'm going to rotate this 90 degrees to the right, and voila. Hello, what you're going to be seeing is a mentoring session I did with Carol in which we go over the binary search algorithm. This video is unedited. If you find parts of it slow, then feel free to skip ahead. Okay, I'm gonna ask Ghostwriter. What is binary search? Binary search is an algorithm used to search for an element in a sorted array or list by repeatedly dividing the search interval in half until the element is found or the search interval is empty. It works by comparing the target value to the middle element of the array. Maybe I should. I'll ask it to. Can you illustrate that? Illustrate the algorithm. I'm making it do my job. Okay. It's not able to draw pictures, as I understand. I think GPT-4 might be able to do pictures, but this is not GPT-4 level. This is Chat GPT level.
Okay.
I'll
have to try that out with GPT-4. I didn't know it maybe had that capability to draw pictures. That's cool.
You need to pay $20 a month to get GPT-4.
Yeah, I have it.
You have it? Sweet.
I'm a sucker.
Cool. Let's see. So diagram that draw. Yeah, I think I wanna pay for it, try it out as well. Okay. So I'm gonna take a look at what it's saying and try to draw the diagram.
Okay. Do you see me in the REPL? Because I'm not able, like usually when I have it open, I can see what you're drawing on my screen, like not the shared screen, but I'm not seeing it today. I'm not seeing the changes.
Try clicking on my avatar and say observe me.
Okay. Trying. Yeah, it's not giving me that option. It's okay. I'll just look through the shared screen on the on Teams. I'll make that work. That's fine.
Okay. So so first, given a sorted list of elements, so you actually have to presume they're already sorted.
Okay.
That's a requirement of this algorithm. Might be faster to draw the lines. I used to have a stylus, but I don't anymore. Well, I don't have it with me. So to get a sorted list of, so let's say I have, I don't know, 1. Okay, I'll do it like this: 1, 3, 5, 8, 12, 27, 50, 68, 100. So it's presumed that you already have them sorted. That's important. Mm-hmm. How you get it sorted, I don't care. You might have to study the array sorting algorithms. Yeah. And then the goal is you want to find a particular value in this array, so that the like you're implementing the find method. So something like Well, okay, not the JavaScript find, because that's kind of different. Maybe I should say like binary, because with a normal array, it's not presumed that they're already sorted, right?
Right.
So you can't have a normal array implement this, but let's say there's a sorted array, and I can binary search find some value. Maybe I want 27. And then it'll give me the index of 27 as a return value.
Okay.
And if I ask it for something that's not in there, then it'll give me a -1.
Okay.
So for 27, it'll be 0, 1, 2, 3, 5, 6. This will give me 6. So that's what we're trying to do. Now it could be more useful if each cell also has attached additional information in it. Then you could use sort of this value as an index into that information.
Mm-hmm.
If that makes, like, if each one was like a person, for example, and then the number was the person's ID, then you binary search find that by the ID will give you additional information about that person.
Okay.
So that's more practical use case. So what Ghostwriter is saying is we're gonna have left and right pointers that point to the start and the end of the list, respectively. So this is the start pointer, and I mean this is the left pointer, and this is the right pointer.
Okay.
And then we're gonna calculate the middle index by taking the floor division, the sum of left and right pointers, and divided by 2. Basically, we're trying to get to the middle, more or less. But because like the reason it's an average, like left at this point is going to be 0, and right is gonna be 1, 2, 3, 4, 5, 6, 7, 8. It's gonna be 8 here. So in order to find the middle, you do take the average of the numbers. So 0 plus 8 divided by 2 is 4. So you end up here.
Okay.
And that's gonna be your middle. And basically you're like, what's the point of this looking at the middle? Well, you can compare your target to the number in the middle.
Mm-hmm.
And if your target is greater than the number in the middle, then you know it's going to be to the right of that. If it's less than the number in the middle, you know it's going to be to the left, right?
Right.
So yeah, so in this case, it is to the right. And then what you're going to do is you're going to replace the left pointer with the middle pointer. So or another way of saying it is you're moving the left pointer to be the middle pointer.
I see.
And then you do the process again. You find the middle pointer again, which should be the middle more or less. But if we were to with the formula, it would be 4 plus 8, 12 divided by 2, which is 6.
Mm-hmm.
I believe that's this, like 0, 1, 2, 3, 5. Oh no, wait, 0, 1, 2, 3, 4, 5, 6. Yeah. This is right. So this is 6, and we're gonna compare our target with 27 with 50, but 27 is less than 50, so we know it's gonna be to the left.
Mm-hmm.
But to the right of the 4, right? Because we already did that comparison. So it's inside this range. So for that reason, this time we're gonna move the right pointer over to replace the middle pointer. So the right pointer is here now. And then we're gonna do the same process again. And we're gonna see that the middle is here now. And we're gonna hit the target. And then when we hit the target, we know that we found it. And in our simple example, we're just gonna return the index of that middle pointer.
Okay.
Yep. So that's the case where we found the thing. Let's try the case where we don't find the thing.
Okay.
So we start here and we start here. We're looking for 45 this time.
Okay.
And so again, we're gonna find the middle. And 45 is greater than that, so we're gonna replace the left arrow. We move the left arrow over here to the middle arrow.
Okay.
And then again, we're gonna take the middle stat, and then 45 is less than 50, so we're gonna move the right arrow to this spot. And then finally, we go here. We see that 45 is greater than 27. And now the right thing to do would be to move the left arrow over and then look into the middle here. But there's actually nothing in the middle because the left and right arrows are right next to each other. They're adjacent. So you can put in a check to see that they're adjacent, that there's nothing in between them. And if that's the case, that means you've exhausted the search. You know that the target isn't in this array, and you return -1.
Okay. Cool.
Or I think this algorithm, let me see. If the target is the same, if the target is smaller, blah, 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 continue this process until the target element is found or the search interval is empty. So yeah, so we can say if left and right is only apart by 1, then the search interval is empty.
That makes sense.
Yeah.
Yeah.
That's the binary search algorithm. Why is this algorithm interesting?
It's a very creative way of doing things. Why is it interesting? It is interesting. I like it. I don't know.
Well,
why.
like it's definitely like, yeah, it's creative. In like it's creative, but what's the gain of, like, what is the creativity trying to like, why are you trying to be clever about this? Like, can't you do it a more straightforward way? Like,
Yeah,
what would be
you could.
what would be a more straightforward way to do this?
Yeah, so a more straightforward way would be iterating through each element in the array.
Yeah.
And this alternative seems like it really cuts out a lot of the work. You know, we don't, going on the principle that we don't want to be searching through elements if we can eliminate the need, like it's eliminating the need to search through large chunks.
That's true. Yeah. So it's improving on the performance.
Yeah.
Or to reducing the amount of work. I actually really like the in computer science, when you're working on performance, always means reducing the amount of work. But I think the word performance in general has the connotation of you're just trying real hard, or like to run fast, or you're putting a lot of muscle into it, or you're putting a lot of power into it.
Yeah.
Because I guess that's what we think of when we think of like performance in athletes, or maybe in other like machinery, or like you put more voltage or a bigger engine behind it, right?
Yeah.
Performance is usually seen as more power. Well, even in computing, you could put more hardware behind it. You could put a faster CPU behind it, more servers, etc. And that is true. But so maybe it's not always true in computer science. That there's this power based strategy in computer science too. But I really like when you're dealing with algorithms and you're working trying to improve performance, that you're actually trying to reduce rather than increase. That's very zen for me.
Yeah, I agree. It's like, what's the way we could do this with the least possible effort or the least possible use of resources? Like it's a cool principle to just think about.
Yeah. So now we want to try to quantify this actually. So like how much less work are we doing compared to the naive method of just looking at every single element? So I want to get the big O of this. First, like, what is the big O of just going through every element and looking at everything?
It's going to be in.
Yeah. So I'm gonna write down. So if just looping through all elements is big O of n. What about the big O of binary search?
Okay,
What's the big?
that one I'm still mulling over, because my initial thought was, if you have a humongous list, you're going to have to do this, and you are going to have to do the process more times. You're going to have to repeat the algorithm of I think, but as I'm sort of saying that out loud and talking through it, I'm like, wait, is that actually true? Here we have.
But you do get an intuitive sense that the more elements still means more work.
Yes, but not.
Like if it was like if we were doing a binary search on 10 elements, you do some amount of work. Again, we should think about worst case scenario. But you can get lucky and then the first try you hit the target, for example.
Sure.
But what if you were doing binary search on 1,000,000 elements? How many tries or how many iterations of this binary search process would you have to do?
Yeah.
What is your? Do you have an intuition about like how much more 1,000,000 is versus 100 versus 10?
Yeah, I'm thinking about it. Okay, so in all instances, you're going to have to find the middle. You're finding the middle. That has to happen every time, no matter what. And then then you're finding the middle of the accepted path. I'm still thinking through it. It just takes me a minute to sort of walk my brain through, okay, the process.
Take your time.
I think, okay, so if you had 1,000,000, you find the 500,000 slot.
Yeah. Oh,
And
let me hold on. I'm gonna write this down.
okay.
So you start with You start with 1 million.
Mm-hmm.
And then your first attempt, you're gonna hit. Maybe I should write it. So binary search for 1 million elements. And I want to say, like, step 1, we're gonna check 500,000 as the middle, right?
Mm-hmm. Yes.
So with step 1, we're checking 500,000. What about step 2?
So step 2, we're going to continue to divide it in half every time. So step 2, we're going to be down to 250,000 elements.
Yeah.
That we still have to look through.
Oh no, I'm writing down the middle pointer. But
I see. I see.
But actually your point is valid, because okay, maybe we say this. So after step 1, then we have 500,000 left.
Mm-hmm.
We could say it like this. And then step 2, we're gonna have 250,000 left, and then after step 3, divided by 2 is like that ish.
Yeah.
Approximate.
Yeah.
And then what is this divided by 2? Like 70
something.
5.
Yeah, we could say
72 5 or
yeah.
72 5 XX.
Mm-hmm.
These are probably XXs. And then the next one, maybe I should consult my calculator. 362 and then
about 15.
That divided by 2, 18. And then we divide it by 2 again. 9,000 something. Let's go all the way to maybe 4,000 something, 45 something.
2.
What did I do?
2250, 2200.
Hold on. Let me move my. Okay. Okay. To what? To 20.
2200-ish. Yeah.
Yeah, 2200-ish. Divided by 2, divided by 2. 1,100. 500 something. 566. 200.
140.
140-ish.
Yeah.
And then 70. We're getting close.
Yeah.
It's 45. Oh no, 35. My son would be into this. Yeah. 17. 8. Then 4. And then 2. And then 1. So it took us 20 iterations to find a needle in a haystack of 1 million numbers.
Yeah. So so 2 things are going on in my head after sort of stepping through this. I want to say, my instinct is to say, that this is still going to be big O of n, because it does grow, the iterations grow exponentially depending on how many you're looking through. But I know that this is much more performant, much more effective than just the straight, what did we call it? Just the straight like iteration, the obvious iterating through every single one. So it doesn't seem right. They would have the same.
Let me ask you this. Hold on. Let me ask you this. First of all, this is worst case.
True.
In the worst case, in order to search through 1 million things, I have to do the same thing 20 times repeatedly. And then the second thing I would make the point of is, what if I want to search through 2 million things? How does that change this answer?
Okay, so then, okay, so we're just going to have more steps because we're starting out at a higher number.
So how many more? We already did 1 million.
Yeah.
1 million took us 20 steps. What about 2 million?
I want to say it's double, but I don't know if that's true. That might not be true. I'm trying to think it out now.
No, take your time. Think about it.
Okay.
Well, if we started with 1 million, and after one step, we only had 500,000 left to look through.
Oh, so it's just one more step. Exactly. One. Every time it's one more. Duh. Because you're dividing in half every time. Exactly. So each time you double the number of elements to look through, you add one step.
Exactly. Now, what about our naive algorithm that go through all the elements? Well, in the worst case, looking through 1 million elements will take 1 million steps.
Right.
What about looking through 2 million elements?
Yeah, it's going to double. It's going
to double the number of steps. Whereas with the binary search, when you double the elements, it only increased one step.
Yeah.
That's insane, right?
Compared to it's a lot better. Yeah. Yeah.
So there's no way you can tell me this is not better.
Yeah, for sure.
It must be much better now. But the question is, how do you quantify this better? Well, let's think. So, you think about how to do this, like, maybe we should think about this. When you look at these numbers, what pattern can you, like, how would you describe this trend? Like 1, 2, 4, 8, 17, 35, etc.
Yeah, it's doubling every time you go up. Like every time you go up a step from starting at 20, our numbers are just doubling every time.
Yeah, if we were to plot it, it would be like 1, 2, 4, 8, 16, 32. It's too high for me to draw it now. So I mean, how would you characterize this curve with a word?
Sharp, like
Sharp.
fast rising. Yeah.
Well, this is exponential. This is 2 to the x, basically. This is equate in math terms. This is 2 to the x, or 2 to the n, if we want to use the letter n, which is exponential. The variable is the exponent. Therefore, it's exponential. But actually, but exponential would be very bad for a big O, and that's not what we have, because it's exponential, but the number of steps we have to take. The exponential is like we're describing the number of elements we're dealing with, not the number of steps we have to take. So as we increase the number of steps, like we were starting with the number of elements before, but now let's do the reverse and say, if I increase just one of my steps, then I can double the number of elements I can take on, right?
Right.
So every time I increase the number of my step, I can double the number of elements I can search through, and that rapidly grows. So it means every additional step gives me so much more power, a lot more, double the amount of power. And so if we want to describe the number of steps that are required to search through n elements, it's actually the inverse of an exponential.
Okay.
So if I ask you, what relative to the number of elements I need to search through, how many steps do you need to take? Then you're solving for make some space here. So given, let me zoom in. Given I want to search n elements, how many steps do I have to take? So that's like the inverse of an exponential. And what is an inverse of an exponential? So you can try to imagine the number of elements is 2 to the power of, how do I write power in this thing? Maybe what I do is 2 to the power of s. So 2 to the power of s, let's say, where s is the number of steps. So number of elements is n. N is 2 to the power of s. I kind of want to do it like, I'm going to try to do it as a superscript.
Okay.
See if I can do that. S. And I'm going to move it over here. Is that?
That works.
That works? Okay. So yeah, n is 2 to the power of s, and s is the number of steps, and n is the number of elements in the array. So my question is, given an n could be 500, n could be 1,000,000, what is the s that you're gonna need? And the math equation for that is s is equal to the log base 2 of n.
Okay.
So if you find the log base 2 function in your calculator, do I have this? So do I have log? Log. I have log base 10. This is log. Oh, like I think you have to do it convert log base 2. And I don't remember how to. I'm not good at math, so I don't remember how to do it offhand. Log base 2. Yeah. There's a log base 2 calculator here I'm gonna use. Or I could have asked, actually, I have 3 free messages remaining. So what is 1,000,000? What is log base 2 of 1,000,000? It's 19.9, which is the 20 steps that we took.
Steps. Yeah.
Yeah. So the equation we're after all along is log algorithm, or the log function, I should say. And a log function is how should I describe it? It's the inverse of an exponential. And it I'll just Google for plot of log function. Yeah, a log function looks like this. Okay. If you plot it, and you can see it grows like this, and it grows very, very slowly. And the more to the right, like that, as the number grows, like to 1,000,000, to 2,000,000, 10,000,000, it continues grow, but it's almost flattens, not quite, but it's growing so slowly. Versus big O of n would just be a diagonal line.
Diagonal, yeah.
That goes like that. So a log line is like this, and that's much, much cheaper. You can just see it.
Yeah. Yeah, so, for sure.
Hey there, this is Toby from another point in time. I have an addendum to make to this video because I thought of a better way to illustrate the log function curve. So this is the exponential function curve as we have plotted. Because the log curve is simply the log function is simply an inverse of this curve, we can actually arrive at that by flipping and then rotating this image. So first I'm going to flip this horizontally, and then I'm going to rotate this 90 degrees to the right. And voila, we have the log graph. So if you remember, we were plotting this guy here, formerly the y-axis, but now the x-axis. We were plotting n, which is the number of elements in an array. And then over here, formerly the x-axis, but now the y-axis is s. So the number of steps required in order to search through n elements. And you can see that if we had to search through n equals 8, say this dot was for the number 8, then the number of steps required to search through it would be 4. And as we double the number of elements, here we go to 16, then the number of steps required to search through it would be 5. And if it's in between, say a number like 10, then we just get a point in between 4 and 5. This is, I think, a much more intuitive way to arrive at the log function curve. So the answer to the original question, what is the big O of the binary search algorithm? Is it's the big O of log of n. Log base 2 of n to be more precise, but that's not super important. The fact that it's log base 2 because it's binary, right? We're dividing 2 every time. You could generalize this to log any number. Like when I asked my son, by the way, this is very applicable to the guess a number game. So the guess a number game is like I'm thinking of a number between 0 and 1,000,000. Can you guess what the number is? And I'll give you 20 tries. Yeah.
But then you have to get the person to tell you whether it's higher or lower than your guess.
Correct. I do have to tell you whether it's higher or lower. Every time. Yeah, exactly. So now when I ask my son this guess a number game problem, his intuition was, well, I'll guess sort of he's thinking in base 10 basically. So he's thinking like, I'll first try 100,000 and then I'll try 200,000. Well, it depends. Like if 100,000 is low, then I'll try 200,000, and if that's still low, I'll try 300,000. Right?
Yeah.
So he's thinking of subdividing it by 10 instead of subdividing it by 2, and it still works.
Yeah.
It's the same idea, but because we human beings are trained to think in base 10, we more naturally gravitate toward subdividing it by 10. But binary is because computer scientists think in binary. So this is natural for them. And so that is why. And I can tell you that this is so related to the guess a number game, with the hint. Every time you get it wrong, you get the hint. And I actually asked ChatGPT this guess a number game. I asked it to play guess a number with me, and it immediately spit out this binary search algorithm to me. Yeah, and but it wouldn't guess a number for me though. I tried to get it to play with me, but it wouldn't. It'll just draw out like, this is what the scenario would look like. Like he spelled out the whole story, but he wouldn't play with me.
Oh, funny. ChatGPT won't play games. All work and no play.
Yes, exactly. Okay, so I guess So usually we don't write the log 2. We just say log of n.
Okay.
And I guess the moral of the story is that log of n is much better than n.
Sure, that makes sense.
It's not even close. It's so the only thing that's better than log of n is log of 1. It's big O of log n is big O of log 1.
I see.
And whenever we want to get something to work super fast in computing, we're always aiming for either big O of 1 or big O of log n. Those are always our best case scenarios.
Yeah, that makes sense. It really does. And I think I intuitively was like, this is way better. There's no way this is big O of n, but I didn't quite have the sort of the mathematical. I'm also not a great mathematician by any stretch of the imagination. So I was kind of lacking the well, what is it? How does this quantify? So this makes a lot of sense.
Okay, yeah.
Awesome.
I'm
Cool.
glad that made sense. Okay.
Yeah, it did. And so this will sort of lead into talking about trees in the near future and in a future session.
Yeah.
Cool.
First, let me ask you, do you have any intuition about how this is related to trees?
Okay. I don't know that I would call it intuition. I have a guess, and it could be way, way wrong. But I know that well, I'm guessing that we use this method to find what we're looking for in a tree structure, that it's going to be tied in together because a tree structure can be big and has a lot of, yeah, I don't know. That's
Yeah.
my best guess.
Yeah, there's a mirroring search algorithm for binary trees. And
Okay,
then, yeah, I think you'll see the relationship later.
cool.
All right.
Looking forward to it. All right. Thanks, Toby. I hope you have a great weekend, and I'll talk to you next week.